Hey, Michael. Um, awesome. So, Michael, thank you so much for coming to talk to us today. And I think Artem, you're the one who introduced myself and Michael, so I really appreciate it. We're sort of a funny group of mostly graduate students in computer science, but I think the funny thing is some of us have now defended, and so it's now sort of mixed between people who have real grown-up jobs and and people who are still in graduate school. But really appreciate you coming to talk to us today. Yeah, this is one of like a pretty decent number of programming language theory kind of talks that we've hosted at this point, including one from Artem and quite a few others. So we're excited to see what you've been working on. So Michael, thank you so much for joining us. And with that, I'll let you take the floor in whatever format you prefer.
All right, sure. I will share some slides and may take me a moment to get the right screen.
Yeah, no problem.
All right. All right. Giving a talk today about an introduction to LiquidHaskell. Michael Borkowski. Uh, Last year, I finished my PhD at UC San Diego, where I worked with Ranjit Jala and collaborated with some of the folks who created Liquid Haskell, including Nikki Vazu. And I am currently an assistant professor of practice at Purdue University, where I do research on software verification and also focus on teaching some core computer science courses like Java programming, data structures, and so on. Okay, so um, I won't assume that anyone's particularly familiar with Liquid Haskell, so I'll explain a bit about what it is, how does the system work, what can we do with it, what are the prospects for using Liquid Haskell, not just to do some lightweight verification, but as a theorem prover, and I'll highlight a few recent developments as sort of an idea of where can we go from here on the theorem proving side, and what are the limitations to that? Is so um, why do we want to do verification at all? So I usually teach languages with static type systems, but as we all know, this doesn't do a lot to roll out a lot of bugs. So here's a line of Java, and even one line of code can contain several different runtime errors. So say in this one line, we could both be trying to say access a field of a null object. We could be doing array out of bounds. We could be dividing by zeros. And so these are typically bugs that are due to programmer error, and they're not recoverable. So there isn't much we can do at runtime because it's not clear what the behavior was supposed to be. So we hope that stronger type systems can allow us to rule some of these out at compile time as well. There are some efficiency gains we could say get around the margin if, for instance, we could dispense with, say, runtimes runtime bounds checking on arrays because we've proven that all of our array accesses are memory safe, meaning we're only accessing valid indices. But with most of the languages we used, whether that's uh, Java, Haskell, or anything else, this is beyond the scope of the type system. So we have array types, but those can't be parameterized by how large an array is. So two arrays of different size will be in the same type. And this isn't just an academic exercise. One of my collaborators here, Joseph Zulo, pointed out this example to me, and I think this is sort of a great example of one of the wins of verification. And so this one has to do with Java. So Java, if you just try to sort ints or something, I believe it still uses a double pivot or single pivot quicksort. But when you give it an arbitrary collection, something that can be compared, then they've implemented the timsort algorithm in the collections API, at least on many of the JDK versions out there. And so this was out for many years, and then some researchers using the Key platform, which is quite a heavyweight verification tool. There's a specification language where you can specify properties of Java code, preconditions, postconditions, and so on. And then that gets translated into a logic. Some things can be automated, some things you have to sit down and write some heavy duty proofs. And so, in the process of doing some work to try to verify the correctness of Java's sort algorithm, these researchers actually found a bug that had never been reported. This could cause runtime exceptions for some arrays of over 67 million elements. And so this wasn't an issue in the Tim sort algorithm, which was fine, but rather in the way that it was implemented, especially when we get to very large lists that preconditions were being assumed that weren't actually being checked or weren't holding. And so there were code paths that could lead to this exception. And so I think 67 million is about the smallest example that was found. And so Key and software verification was able to go in and show that yeah, look, here's some real code that we've actually found a previously undiscovered bug, and we've been able to develop a suggested alternative that isn't vulnerable to that. And so that's there's a lot of heavyweight stuff with that, but one thing that I'm interested in that it has some more applications to more lightweight development where we don't have to write a lot of proofs are refinement types. And so that's the idea that we're going to uh, get more specific than just an int in Haskell. Instead, we can write a sort of this set comprehension or set theoretic notation that will express some kind of predicate. And so here, for instance, have an expression for, say, the type of all integers strictly between 0 and 20, so from 1 through 19. And so these will be Boolean expressions. And so, in theory, these can be arbitrary things. In terms of a language, you can implement that with some type of syntax. And so, as I mentioned before, functional correctness and especially preventing some of these runtime errors like array out of bounds are some of the chief uses of this here. So if we went and built a system with refinement types, what does that really mean for type checking? Well, the two sort of key things here that we have annotations, let's say arbitrary types, and Haskell functions are these types connected by arrows. So a refinement on an input to a function is a precondition. It's a contract that says the function will only take this specific type of element at a postcondition. That's a promise that our function will output elements that satisfy this predicate. And so function calls are the main place that we need to be worried about checking refinement types. So if we can infer a type for every element, I mean, it can be its Haskell type with a trivial refinement, and then we have to check at every function call, do the arguments satisfy the preconditions, and then inside the function bodies, does the return value satisfy the postconditions? And so what we get here, or in fact, we can write verification conditions, meaning we can translate this extra work after we've done our Haskell type checking into logical implications. And in principle, we can pass that off to an SMT solver to try to go and verify that. The issue is that in general, this kind of satisfiability is undecidable. So inconclusive type checking is not at all desirable because we don't want a programmer to have to do all sorts of kinds of guesswork to get a program that's probably right to actually return checks or unsafe. We want something to return 100% of the time. And so liquid types were invented to restrict those predicates to a decidable logic. And so this seems small, but it's good enough to verify quite a lot at Haskell. So we have Boolean propositional logic. We could use all the Boolean variables to make complex predicates, we can add in the what we call the quantifier-free linear arithmetic. So refinements can't themselves be quantified expressions. Otherwise, we could say do a universal quantifier over all of the integers and potentially have an infinite number of different things we have to check. And we can also add in uninterpreted functions, meaning that we can refer to functions in our program. So we'll take a look at some of these in a little bit. So these kinds of systems have been built on a lot of popular languages. Some of these have a much bigger community and a lot more support than others. So on the left, particularly Liquid, Haskell, and Flux have a lot of support, and Flux has gotten a lot of attention recently, but we aren't in principle limited to just those languages. So there's been projects to add refined types to C, liquid types to Java. If you step out of the functional paradigm, then in that case, you're looking at specifying things often like loop invariance and reasoning about the state of something over time. Liquid Haskell is especially nice because when writing pure functional code, we can just be worried about like the input output behavior and sort of this mathematical specification, and we don't have to worry about state. But to get practical adoption of these systems, we need lightweight verification. Library developers aren't going to add liquid refinements to their libraries unless this is easy to do and they don't have to spend dozens of weekends, say, adding proofs throughout. So Liquid Haskell, using it has gotten a lot easier in recent years. It's been available with G8C as a plugin since 8.10.2. And so using a tool like Cabal, that eliminates the need to go and download and build Liquid Haskell yourself. The system will run as a phase during compilation. So you'll have the G8C type checking to ensure that you've at least you're able to compile as a Haskell program. But before that kind of compilation actually happens, then Liquid Haskell will run and we'll check any of the refinements in your program. So if you're starting a new project, it's as simple as adding less than 5 lines to a Cabal file. So you can specify with GHC options, you can add this to your list of plugins. I like to hear, for the examples, I'm assuming reflection is turned on because we'll want to talk about deep verification where we can reason about user-defined functions. And then Liquid Haskell and the Liquid Prelude are really the only dependencies that we'll need. Your project may have base already. So I've linked to a GitHub repo here, and we'll be going through the sorting file shortly. So I can try to drop that into the chat in case anyone would rather follow along through the code in the bubble sort file there. All right, so we're getting closer to some examples, but I'll sort of break down the main things that Liquid Haskell can do. So we've talked about verifying functional correctness of code, but in addition to that, things that aren't strictly correctness that are important are that we can verify the totality of our functions, and that can mean in our pattern matches as well. So with regular Haskell, if we know that, say, a list is non-empty, well, we can break that down and match it into a head, cons with a tail. But in principle, there's going to be a runtime error if an empty list ever appears and we only have a pattern for a non-empty list to cons to match it on. And so Liquid Haskell can prove that situation can't occur. Termination checking of recursive functions as well. It's not always easy to prove this in different systems, and it may not always be obvious when a recursive function would in fact terminate. And then we can prove things that are less properties of code than theorems specifically. And here is sort of a informal definition of theorem. I'll use that to refer to a code that's never meant to actually be run, but it's just being used to establish a property that can be verified by Liquid Haskell at compile time. Okay, so with functional correctness, my collaborator Nikki Vazu has sort of broken down verification in LiquidHaskell into sort of two types of levels. And so at the light verification level, we may go and write a simple specification for a function. You can think of going through a library that you have and adding refinement type signatures to make explicit checks on the preconditions and postconditions that are assumed by each function. If these just involve simple restrictions to the refinement types, then further proof work may not be needed. And so this is the kind of light verification that we hope gets wide adoption. But what I'll be showing you is an example of more deep verification where we want to define and prove some semantic properties of programs. And so that can be like sortedness, that we're going to preserve the set of elements in a list and so on. And in order to do these, we'll need to define what properties we need, lift them to refinement logic, and then start proving properties about that, because a lot of things we don't get for free. SMT solvers could help us with some stuff, but we'll see where sort of the gap appears and we need to begin writing lemmas. So as an example, I've chosen maybe not the algorithm you expected, but if we wanted to just sort, let's consider a bubble sort variation. This one, it's not too much of a stretch to consider if we're using Haskell's built-in lists, because bubble sort only uses the swap of adjacent elements. Haskell, we essentially are dealing with linked lists, and so we can do that without having to define and argue about operations to index into arbitrary elements. Typically, I found each version of bubble sort, you typically go through, take one sweep and sort of bubbles sort, meaning you swap an element to get to the end of the array. So conventionally, we might go through here, look at neighboring elements, swap to get the larger one on the right. Because in Haskell we have access to the head, I found that it was more feasible to verify one going in the other direction. So I'll consider a sort of left variant of bubble sort where we will bubble to the left. And so the basic approach is that we'll consider the list on any call, we'll take a sweep through the list, we'll do recursive calls. So our start at the bottom, and then as we go up, we'll bubble the smallest element to the left. Then, while we get the smallest element, cons a bunch of other stuff that may have been shuffled around, but we'll make a recursive call to sort this smaller list. So for instance, if we started, say, with this list here, the bubble up process would make recursive calls till the bottom, and then we would look at, say, 5 and 2 as the last elements. Well, 2 is smaller than 5, so we make a swap right there. And then we would go back through the list and compare neighboring elements. Well, 2 is not smaller than 1, so we don't need to do a bubbling. Next, we have a 4 in front of the 1. So the 1's smaller, so we'll bubble that to the left. And then we'll bubble up the 1 past the 3, and then we get the smallest element up front, and we can recursively sort the list. And so when we look at verification, we'll have to think about what is sort of the invariant here. But essentially what we have is that if we consider this iteratively after k bubble up operations, we would have the first k elements in sorted order. All right. So this is going to be an example of deep verification because with simple refinement logic, there's not an easy way to specify the kind of properties it would take to prove correctness. So what we would need to know here is, we need to know that the output list is sorted. We need to know that it's also the same multi-set of elements. So I could trivially give you a sorted list. I could just return a list containing only 0 all of the time. You could also add as well that the length of the list is preserved. That's going to essentially be implied by the second point here. And I won't really mention it other than we can get that one for free. So for the rest of this demonstration, I'm only going to consider sortedness for simplicity so that we have one objective to look for. And now sortedness, well, you could think of that if you define this in another theorem prover, you might say, well, for all indices I and j, if I is less than j, then the corresponding elements must be less than or equal to. But we're dealing with decidable refinement logic here, and so we can't express sortedness in that manner. Instead, what we can do is we can define a recursive Haskell function, and then we will have to go through and reason about that. So yeah, here, take a look at sort of a function like this. And sortedness, this one will be a little more maybe complex than other properties you might want to reason about because this one involves looking at two elements. So sort of a recursive definition for sortedness um, is to see if your list doesn't have two elements, then it's certainly sorted. If your list has at least two elements, take a look at the first two elements. If the first element is smaller than the second, at least as small as the second, then uh, you're okay so far. And then you can check elements pairwise on the tail, just chop off the first element. However, if the first element's not larger than is larger than the second, then you know that you have an issue here. So that's captured in the x less than y, so that's how we can falsify this. In order to do this recursively, then in full generality, this can check a range of an array as being sorted. And so if we have a trivial range, then we'll say if we have a trivial range, then we can say that it's sorted automatically. Otherwise, we have to make sure we have at least two elements. And if we're looking in something further down, then we can just recurse by looking at the tail and reducing the indices. But when we get to the range that we want to start verifying for sortedness, that's when we would check it. So here, this is just a function that returns bool. And so one issue with that is that all of these properties that we talk about do have to be computable. So we can't easily or in ways that we know reason about, say, uncomputable predicates. We actually have to define that as Haskell code so that this could be run. It won't be run, but in principle, could be run. And because this uses sort of basic Haskell constructs, it is recursive, but it has no recursive helpers. Then this is eligible to be lifted to the refinement logic. And so what that means is that using this directive here in a liquid annotation, we can talk about is sorted between in our refinements, and then we can begin to do some deep verification. Right. So then that means that if we want to take, say, bubble sort and prove that it's sorted, and here this one has a simpler definition for the algorithm than for the property that we're trying to prove. How bubble sort works as well. There's nothing to do if we don't have at least two elements. Then if we do, well, we'll take our list, we'll do the bubble up process I mentioned, that number one, that's our y, it goes at the top. And then everything else, well, it's bigger than the y, but we don't know what order it's in. But if we recursively sort the tail, then the tail is just been shuffled, so y is still the smallest element, and we get a sorted list. And so the key here is to put together these two facts that now we have a head that is the smallest element, everything else is sorted, but we've got to use the structure of this definition. And so we're not able to make intuitive or sort of informal reasoning. And so actually stitching these facts together is where some of the effort lies. I think I spent maybe 2.5 hours of work on this example to sort of give a metric. Okay. Before I get to scrolling through the code, a few other interesting things here is that totality checking was on the list. And so This will come up in various pattern matches, but for instance, the classic example is on a head that with regular Haskell, we would need to write a branch with some kind of error message. Otherwise, GHC would complain. But with Liquid Haskell, we can take what we're assuming that head is only defined on non-empty lists and go and make a precondition. And so here's an example for precondition. And then we can actually delete that first line of code and GHC won't yell at us about that because Liquid has proven that this function is total, even though we're not dealing with the nil list case at all. Termination. And so in here, I do have an example of a non-trivial termination proof. And so the idea is that Liquid Haskell has some degree of ability to check termination of functions. In particular, it looks at what are the recursive calls. And so if you're always doing a recursive call on a smaller natural number, that's an easy check. For data types, it can look for which position argument is strictly decreasing, meaning if we have a tree and that's an ADT in Haskell, and so all of our recursive calls are on substructures, pieces of the pattern that we matched, then Liquid knows that that is a recursive call. Beyond that, for instance, if Liquid can't figure out which argument we're supposed to be decreasing on, sometimes we have quite complicated termination conditions, or we'll have to state a metric for Liquid Haskell. And so that's a mapping from our data into the natural numbers, or even into tuples of natural numbers. So Liquid Haskell has lexicographic termination built in, and so you can easily show the Ackermann function terminates. And so that's a function that grows very large. And in Coq, for instance, it takes some extensions in order to be able to actually prove that, because you need to have something that where you can argue about the well-foundedness of different metrics. And so lexicographic order isn't a easy built-in thing there, but Liquid can reason about that. And so let's go back to the bubble sort function. And here we do have a termination metric, because the recursion, I described it, I glossed over it, but it wasn't quite so easy. Well, the reason for this is that the recursive call is not on the tail of the list. The recursive call is on the tail after the bubble up. And so what we're sort of passing over is that, well, bubble up just shuffles items around, so it preserves the tail list. And so it sort of makes sense to talk about the tail post-bubbling as being equivalent, because it's still the length of the list -1. And so when we define length here as a termination metric, then Liquid can infer that as long as we have the correct refinements to establish that the post-condition of bubble up, that the length is preserved, then that can go through. And so that will sketch most of these things here. There's a few corners. So I have parameterized this over arbitrary types A inside our list that have an instance of ORD. And so these are be any kind of comparable type. In Haskell, one thing that's easier than using ints is that you don't get your elements confused with your indices in a type signature. Another thing, though, is that we haven't actually proved anything about the correctness of the ORD instance. In fact, the code doesn't talk about it. And so, that may be seen as a gap as well. And so what happens there is, well, if we go and we lift this definition into the refinement logic, then because our SMT software can decide among the various things we've combined, linear arithmetic does include inequalities. And so this can sort of actually get embedded as the liquid Haskell, as the SMT level, say, inequality. And so there's a sort of a little bit of a disconnect. But so far we can consider here, and we'll take a look now at uh, example of the code and how that works. So I will switch over to this editor. And so we've been through the shell of the code, but haven't say talked about the proofs yet. And so one thing with Liquid Haskell that we do is that we can, if we need to talk about a specific function, we can define these as recursive properties and lift them to the refinement logic. So the syntax checker doesn't particularly like sort of these symbolic infix operators. And so here we can define cons to mean the same thing as the normal version in Haskell. So we've shown you these ones here. Now we've got one more pair of properties that expresses the sort of the invariant that once we've done one round of bubble up, the head of the list that results is less than everything else. And so we have a lemma there that we can extend that. If the head's less than everything else and something's even smaller than the head, then that's going to be smaller than the whole list. And so the typical approach to a lemma here in Liquid Haskell is that it provides us some types, and ultimately the output of a lemma, it's a proof term, but it's not meant to be run. Liquid Haskell gives us the type name proof, but in reality, this is just a synonym for the unit type. So this is just the unit type. And so it's not actually doing any useful computation, but the reason is then what makes it actually a proof is that this unit type carries a postcondition, which is the theorem statement. So given these hypotheses, this is the theorem conclusion. Now, the only value of the unit type is itself the unit, and Liquid Haskell gives us trivial as a synonym for that. Now, proofs in Liquid Haskell, so we don't have any kind of tactics, we don't have any kind of interactivity. Rather, we can follow sort of the heuristic, which is that basically everything that we're arguing about is recursive, and so we can get some structure to start with by following the same kind of recursive definition. So an element below all, if I want to check that X is at least as small as every element of the list, then I can do a simple recursion on the list. And so our lemma can have that same structure. And as our arguments have a more complex recursive structure, then that will be expressed in our lemmas. So I'll mention here that there are generally sort of two proof styles. And so this was identified by Nikki Vazu and collaborators in some early work comparing Liquid Haskell to sort of the versions of Coq at the time. And in those are sort of intrinsic style and extrinsic. So we'll look at say bubble up here. And so an example of an intrinsic proof is that we want to do some kind of a deep verification, and we want to check all of these properties sort of without going and writing a lot of extra functions. And so the key here is that, well, the property that we're actually trying to prove, so for bubble up, that the result has the head is smaller than the entire tail of the list. We can express that directly as a post condition. And so this is called intrinsic because the proof that this refinement actually holds, the proof itself doesn't have an explicit term. So you don't go and construct a term that you can see. Rather, everything is sort of ephemeral and happens in the SMT solver. And so in particular, Liquid Haskell then checks this in terms of how we do the case breakdown. And so here I'm using equational pattern matching. And so that is syntactic sugar. I could have written case of for all of these definitions. So for instance, for say the bubble up, we'll assume the list is not empty, and then we'll do a case split to see if it has two elements, and then we'll recurse all the way to the bottom of the list, and then do that pairwise swap. And so here, there isn't really, the only sign that there is a proof going on is that I'm bringing this lemma here into context. And so this lemma here is written as a function so that it is able to essentially do a universal quantification. I can then say, well, I'm interested in showing that x, which is the head, is less than the head of the recursive call, and that recursive call is smaller than this whole list. Uh, LiquidHaskell has two operators with proof and a question mark that you can use to sort of introduce these terms. So this is a unit type, and with proof, and we'll also see a question mark, those will just return the first element. So it ignores the second element, which means that even if computation was going on, then that's code that GHC can optimize away at compile time, so it would never get run anyway. But the important thing is that this is in the theorem, and so then that LiquidHaskell knows that this implication is true, and that can be added to the SMT query in order to verify that the post condition is satisfied. And so this is one way you can write theorems and proofs in LiquidHaskell. It is quite compact. The disadvantage, though, is that you can't necessarily express a lot of the properties, say you want, in this way because you are limited to properties that are sort of post conditions that are in terms of your elements. If you have another property, and I'll show you an example here, then it may be necessary to state our lemma separately, and it may also be helpful for ergonomics, because you can imagine here that, well, I've got this property, but then if I was doing like the full 100% proof, I would also be showing that the bubble up doesn't change a multi-set of all the elements, and so I'd have a predicate for that. And then it can become a little bit more unwieldy because we've got multiple different refinements being proven, and there's different citations for different ones. And then this can create sort of a somewhat brittle state because it can be sort of hard to tell exactly where the error is when LiquidHaskell says, okay, this thing here, or maybe this branch doesn't satisfy one of the predicates. Finally, you'll note here that the length being preserved, that's something we got for free. It wasn't for free, it was an intrinsic proof, but there wasn't really anything non-trivial going on in the recursive case. LiquidHaskell can tell that we had no change in that. So ZS and YS have the same length by induction, and then this is that length plus 2, that length plus 2. Okay. So the extrinsic style, this is one that becomes a little bit easier. Well, becomes a little bit more verbose, but it can become easier to tell where your errors are because it's more modular in the sense that we're going to express our lemmas separately. So here, I am not going to put is sorted in this example into the post condition. Rather, the function will be written with only the stuff that we can get for free. So this is still an intrinsic proof, but now I want to make sure I can reflect it so that I can write lemmas that talk about bubble sort. And in particular, then the key lemma here is that the bubble sort is sorted, and so this will prove the property, and then we can refer to this by calling this lemma in another situation whenever it's necessary. And then down here we can see that, well, for an extrinsic lemma, we don't actually have all these cases for free, so I have to make an explicit case split and basically copy the structure of bubble sort. And so these two would be trivial, so I can make these trivial for consistency, even though this is just a synonym. And then we can then express that fact before. So we call a lemma that says, well, if X is below everything in the tail and the entire tail is sorted, then that thing we put together is sorted. And so it then takes a lemma to prove that. So those are two sort of specific styles that we can use to reason about LiquidHaskell as a theorem prover, finally, we have made a few non-trivial changes to the code. So then we can go and run Cabal. And so here we don't need, say, stack or anything. I showed you the core part of the Cabal file. And so first it'll do the GHC checking, then it'll check any files that have changed. And since it's reported to me that this is safe, then we can see in source, I think Cabal builds it somewhere else, but we can see we could then go and find and see that that file was actually built. It passed checking. All right, so um, we've talked about the intrinsic and extrinsic style. What other difference in style or approach we can take? I've looked at this mainly the second point here. The older style of LiquidHaskell allowed us to do explicit equational reasoning, meaning we could write a proof as a sequence of different lines, say starting with one side of a refinement and transforming it to the other side using an operator that would check equality on each line. Um, for since about 2018 or 2019, and over time, the proof biological evaluation module in LiquidHaskell has really improved. And what this does is that it allows us to sort of take full advantage of automation. We don't have proof state, so we can save a lot of time on having to write out explicit proof terms. And in Coq, you would never go and write all these out. Rather, you would just use tactics and see on the screen how the computer uses those to rewrite your goal. But we can allow LiquidHaskell to augment the SMT instance with unfoldings, so say the reflected definitions it knows and these various terms. And so that means that there's quite a lot of stuff going into the SMT instance. And as our functions and proofs get larger, that can increase the time it takes because there is an SMT solver running many queries to verify each one of our files. So I've talked about the intrinsic and sort of extrinsic style. And so that shows we can reason about some of these properties that, assuming I've defined sortedness correctly, then I can prove that our definition of bubble sort respects this definition of sortedness. And so we can define a lot of stuff like that, especially for reasoning with programming languages. We can define, say, Boolean valued predicates, sort of imitate some of the props in Coq. But one of the things we run into is the question of can LiquidHaskell ever compete with established industrial strength proof assistants? And for those, we'll take, well, Rock has recently become the new name for Coq. So we've got Rock, we've got Lean. I understand next week there'll be a speaker to talk about Lean. So I'll make sure to come back and hear that talk. So if you want to compare LiquidHaskell to these, well, there is some pretty sort of key things missing that currently sort of keep it from being used as a theorem prover to the same degree. And so sort of in order of importance, the number one is interactivity. In a way, using Rock is almost sort of gamified because you've got an explicit list of goals. You can check it off like a to-do list. You could use combinators on tactics to help automate it. You can throw tactics at these goals, and you have sort of an idea of the proof state. So if I'm stuck in a proof and some lemma's not working, then I can, without too much work, see like what is the difference between sort of the term I can establish and the proof, the goal, the fact that I need, and sort of see where is the mismatch. And so without interactivity, we sort of get one shot at this here. So for instance, hopefully this is switched back to my editor. If I go here and say just chop off one lemma citation from my code, I should show you at least one error message. Then, well, when I run LiquidHaskell, it will go here, and then it'll give me a sort of an error message that's a little bit cryptic. But what it does give me is it can give you a little bit about what it can infer. Sometimes this is useful, but you're not going to get, say, a way to see all of the equations that we know, what's in context. Rather here, because it's outlining a specific argument, that means that bubble sort of ys doesn't satisfy the precondition that it has to. And here, in fact, there's two preconditions here, and the error message narrows it down to one. And so by structuring things as sort of conjunctions of refinements, you can sometimes get, you can usually get which part is not satisfied, but there isn't really a look at the proof state. And so that makes it harder to be able to deduce sort of exactly where things get wrong. Finally, sort of what's missing is sort of the generality to do the full software foundations is that nothing I've shown so far allows us to reason about potentially non-terminating computations. And so these aren't just things that are not terminating. These are things that we can't prove is terminating. And so, for instance, the semantics of a language like the lambda calculus, if you add a simple type system, a simply typed lambda calculus, that is well known to be strongly normalizing, meaning that every well-typed term evaluates down to a value. So the semantics are finite. In a finite number of steps, every term will reduce to a value if it's well-typed. And the issue with that is that, well, we can't define a recursive function to compute, let's say, step of some lambda term because we can't prove that that function actually terminates without doing a whole lot of meta theory. So I'll finish by sort of talking about some approaches in recent years, sort of to each of these. So to the first point about interactivity, fundamentally that would sort of be very difficult to get around without, say, completely designing the system to put a whole system to stand between LiquidHaskell and the SMT solver. So I think fundamentally for now, we live in a world where the automation provided by an SMT solver as our prover is one shot, but we can make our life a little bit easier. So Henry Blanchett, Nikki Vazo, and Leonidas Lampropoulos wrote a paper at Haskell in 2022 called Liquid Proof Macros. And so they looked at using template Haskell, which is a meta programming system for Haskell, to expand macros into proof terms. So like those proofs I showed you, where you've got multiple equational definitions, desugared, that's a case split on various arguments, if thens, it ends in trivial or it ends in some lemma citation. And so if we could, they found ways to imitate certain tactics like induct. And so if you call induct on a specific argument, then that will expand into a case split. And so that system can, they found, handle in fewer lines proofs from a wide variety of benchmarks they looked at. And that's something that's separate from LiquidHaskell. So it doesn't introduce any worries about is the sound, because it essentially template Haskell runs the pre-processing step. You can actually see the file with the proof terms that are output, and then those proof terms are either valid or not. So a bug in the meta programming isn't a bug in LiquidHaskell. One thing that SMT solvers promise that LiquidHaskell hasn't been able to deliver yet is counterexamples. And so essentially the SMT satisfiability problem, well, if we can't show valid means it's unsatisfiable because we've negated the whole thing. But if we can show that our program is unsafe, then we get a formula that is satisfiable. And so there's some kind of counterexample, but that's really hard to thread all the way through LiquidHaskell back to the user. There's a lot of syntactic transformations that go on at intermediate stages, things that are rewritten in search and normal forms. There's lots of stuff that go into the SMT formula. And so that's not really something we can easily translate, especially because the LiquidHaskell system can continue to develop. So a different approach taken by Webers, von Gleisenthal, and Jala at UPSLA last year, they called refinement type refutations. And so they've been working on a system that extends LiquidHaskell and has techniques to sort of use the data left behind by LiquidHaskell to look for a counterexample. And they found on benchmarks most of the time. They can get something for the user. And so I believe that they're working on sort of a tool that could help the user. You don't get true interactivity, but you might sort of get it back and forth. Like you could get some useful information back, like here's a better indication of why something failed. Finally, work that I was involved with for non-terminating tech computations is a technique called refined data propositions that can allow us to make arguments without having to write everything as a terminating Haskell function. And so this idea is to try to create in LiquidHaskell something that's a near equivalent to the rock style inductive predicates that are used. And so this was included in work in collaboration with Nikki Vazu and my advisor, Ranjit Challa at Hopple in 2024. And so this part of the work was sort of the first presentation of this technique to enable LiquidHaskell to do many sort of PL proofs that are from like pure style types of programming languages or from software foundations. And there, one of the strengths of the ROC system and LEAD as well is that we can express propositions as types, meaning that our types can be parameterized by values. In Haskell, the GADT extension for generalizing ADTs, we still cannot parameterize a type by term level values. So what we have to do is use a separate type and then come up with a way to relate it. So suppose that we had a proposition type, and this will say just hold all the different propositions. And so we can then construct values. Our propositions will be values, and we'll use refinements to relate them to proof values. So for instance, in the semantics of lambda calculus, we could say some expression E and E prime are related by step. So step E, E prime, that's a value of the proposition type. And then we can encode our proof trees as ADTs in Haskell, and that'll be sort of a direct translation from Rock. So then the key, what we added to make this technique is a few lines of a boilerplate where we relate specific propositions to specific families of proofs, meaning that given a proof, we have an uninterpreted function prop of that says that, okay, this is going to be proof for a specific proposition. And so with an uninterpreted function, that means the only way that we can construct proofs are when we explicitly say we can. And so for instance, a proof of E is then a type synonym for saying these are proof objects whose proposition is E. And then we use proof of as postconditions when we're defining inductive data types. And so the refinements on everything but the last argument, those are preconditions that restrict when we can use the constructor, but the postconditions are taken as assumed. And so that's how we can create proof trees and start doing a lot of these PL proofs in LiquidHaskell. I did about 10,000 lines of this in my thesis to show that it was possible to do it in both systems. However, there are some limitations. So when we're doing inductive propositions, these inductive data types, they have to be checked for positivity. Coq has a strict positivity checker that's been implemented in LiquidHaskell as well. And so that avoids unsoundness. However, some proofs are not possible with this technique. And so there's a few proofs mentioned in software foundations. And so in the programming languages portion about strong normalization, there's a discussion about how we can't use that technique in Rock due to that kind of proof. And instead, we have to write an ugly fixed point on props and sort of argue about that. And so something like proving the strong normalization of the simply typed lambda calculus, that's an example of something that's beyond the frontier in LiquidHaskell, on that it would take some further techniques in order to make that possible. So I've reached the end of what I want to talk about. I want to thank Max for the invitation. I thank my collaborators, Nikki Vazu and Ranjit Jala, for their help on the work I've talked about.
Michael, this is fantastic. Thank you so much for taking the time to talk to us today. Do you have time to do like 5 to 10 minutes of questions?
Yeah, I can stick around for some questions.
Okay, well, maybe I'll get us started, and then if other people have questions, please just hop in. My experience, my background's in ACL2, and like my experience with ACL2 and also a little bit with Ivy has been that the nature of the prover like ends up really changing the way you write the code you want to prove stuff about, right? Like you know what the strengths and limitations
Hmm.
are. So I was just curious, like, in what ways does Liquid Haskell kind of encourage and discourage different styles of programming?
That's a good question. So, having done like the same large proof in both systems, one thing I went through and found, which is like, oh, some things are, more feasible, more doable in the rock system, but other ones were a little bit better in Liquid Haskell. So when I went through here and mentioned things, even in the extrinsic style, things we get for free, and so when we have functions sort of that act on, say, terms of the programming language, like we have to start reasoning about variables, free variables, bound variables. We could start building Haskell functions for that. We can get stuff for free. And so SMT has a strong theory about sets. And so I found it was much easier to deal with juggling and stuff about like the set of variables. So for instance, you argue that if you open up De Bruijn index in a term to a certain variable, then the set of free variables increases by that variable, and so on. And so a lot of the stuff I didn't have to worry about as much because I could just park all of these as post condition complex post conditions on the free variable function, and that would get passed around. While as in Raka had to do hundreds of lines of arguments about simple ideas about set intersections and unions. Liquid was also really nice about mutual recursion, and in particular, you could have mutually recursive functions. You can have mutually recursive inductive data types through the refined data proposition. And so the induction sort of got past what Rock can do by default. And so that meant tactics got sort of a lot messier because you had to explicitly do the induction over multiple, say, over all of these at the same time, and then write other theorems that then specialized it to just one type. So it does, yeah, influence sort of the style a lot. And then sometimes you get as well that the style of the code you're arguing about, sometimes you want to go and sort of alter that to match to make the proofs easier to go by, and so then that can be sort of a little tricky when you can't alter the code as much. These things tend to be pretty brittle to code changes.
Daniel, did you have a question? You unmuted, but I wasn't sure. Okay. Yeah, I don't know. Your point about like brittle to code changes, like even a simple one is just with you brought up like the reverse, bubble sort, right? Like
Right.
in Lisp, like one direction of induction can be really easy, and the other can be just a phenomenal pain.
Mm-hmm.
And so definitely that resonates
Mm-hmm.
with my
I,
painful graduate experience as well.
You're right. I changed it to this bubble up left-sided bubble sort specifically to avoid having to use or write or reflect indexing operator.
Right.
Like
That makes
once
sense.
once we have gets and sets in our theory, then we can go and write stuff about them. But the even the invariant for the normal bubble sort to the right, it can't really express it with the tools I have. I would need to develop more theory to say that everything is smaller than beyond the kth
Right. Um,
than the kth element specifically.
Unless Micah or Arjun have a question, I guess like maybe one last one would be, do you foresee kind of an interesting like interplay to explore between runtime versus provable properties? Like I could imagine you have some things that are undecidable or maybe just like incredibly inconvenient to prove, and you make them runtime properties, and then you try to prove that if those hold, then like some other things hold, and you do that in a more static way. Is that something people do? Is that interesting to you? I don't know. Could that be done within Liquid Haskell?
Uh, there are systems that sort of predate Liquid Haskell and the idea of liquid types that had sort of a hybrid approach. And so I think the earliest paper on this was from Cormac Flanagan around 2005 about he called them like manifest contracts. And so there, the checker, because things are sort of undecidable, if you can't verify it, you can't assume it's false. And so it would insert essentially runtime checks and casts
Mm.
into the code. And so things in an undecidable theory that couldn't be handled by the prover would then sort of turn into these runtime checks. And so that could mean that you'd have like these explicit checks. And so you'd have a kind of like hybrid safety on code you ran,
Right.
but you wouldn't really know anything about invocations or code and calls that you didn't run.
Yeah, that's interesting. Okay. Well, Michael, thank you so much for joining us. And yeah, this is fascinating work, and I'm I think it's pretty likely you get emails from people who, watch the talk after the fact. So
Mhm.
I assume they can just go to your academic webpage, just linked from our site, right? And email you at whatever your address is.
Sure, that's right. Yeah, I've got my email at Purdue, and so yeah, anyone watching is welcome to email about any further questions.
Yeah.
Awesome.
Where is this talk going to be posted?
Oh, so it'll be linked from our website, bstn.cc. Michael, if it's okay with you, I'll put it on our YouTube page, and
Sure.
then I'll just link the YouTube from our site. So it should be easy to find.
Okay, awesome. Thank you so much. Yeah, I
Yeah.
really enjoyed the presentation. And also you had some very good questions after Max. So
Okay.
overall it was a great experience. Thank you.
Awesome. Well, you're welcome to come back to more in the future if you enjoy them. Just shoot me an email and I'll give you an invite.
Okay,
Okay.
thank you.
Thanks, everyone.
Great talk. Thank you.
Bye.